In this final calculus lesson, we're going to look at some three-dimensional problems and how we can optimize those kinds of situations. So kind of an extension where we left off in our last lesson, just dealing with somewhat more complicated problems. So we're going to start off with a closed box. Wood is 4x centimeters long, x centimeters wide, and h centimeters tall. So on our little picture here, 4x, x, and h. And we know the volume of the box is 320 centimeters cubed. And we know we can build an equation for volume. That should be length, width, height. In our case, 320 equals 4x times x times h, which you can simplify into 4x squared h. Okay, so part A says write down an equation. Well, that's what we got there. And then show that h equals 80 over x squared. Well, how did they get that? Well, if we divide one side by 4x squared, we can divide the other side by 4x squared. And we'll end up with h on the right, and 320 divided by 4 makes 80 over x squared on the left. Okay. Part B, write down an expression for the surface area of the closed box. So surface area is the sum of all the surfaces, right? So we've got, if you think of this as a front and a back, they're each two of them, and they're both 4x times h. Okay, think of it as 4x, and they're h tall. And then we've got our two sides, and they're, as you can see here, x by h. We've got two of them. And then we've got the bottom and the top, and those are each 4x by x. There's two of them, so 4x squared. We're going to simplify that a little bit. We'll get 8xh plus 2xh plus 8x squared. Or in other words, the surface area can be given by 10xh plus 8x squared. Yeah, that's it for the surface area. Part C, I want to find the value of x, which makes the surface area minimum. Now here's where we come across that calculus stuff. Minimize. Optimal value. Turning point. I want to minimize my surface area. So in other words, I want to take a derivative of my surface area and set equal to 0. The only problem I see in surface area right now is I've got two variables. But the nice thing is I can take the h, which I solved for in part A, and replace it in part B. So we'll end up with surface area equals 10x times h, but we just said that h is 80 over x squared plus 8x squared. Now this is not a nice way to set it up to take a derivative, so let's simplify a little bit. Let's multiply in the top, so we'll get 800x over x squared plus 8x squared. We're just going to multiply these two things together. We can cancel an x from the top and the bottom with a fraction. So it simplifies it a little bit. And because we know we're taking derivatives down the road, let's get rid of that negative, the fraction by using a negative exponent. Okay, so all that work I just did was to set this up to take a derivative because I want to minimize it. I want to know where my surface area comes out to 0. So, good old derivatives. 0 equals, okay, power law, negative 800 x to the negative 2 plus 16x. We'll refix the exponent, so it makes it easier to work with. We'll put numbers on one side and letters on the other so we can cross multiply. We'll then cross multiply, so do it this way. We'll get 800 equals 16x to the, got an extra exponent in there, sorry, x to the 3. If we divide both sides by 16, we end up with x cubed on one side and 50 on the other, which means we can get x by taking the cube root. Okay, so just to show that, x will be the cube root of 50, which gives you approximately 3.68. Okay, the question was, way back up here, find the value of x which makes the surface area minimum. So therefore, the surface area is a min when x equals 3.68 centimeters. So I didn't ask for it, but we could go back and figure out height using the h equation. We figured out in part A. Or we could figure out the volume if we really wanted to, because we'll have x and h. Okay, that's kind of how we deal with three-dimensional problem solving in calculus. Okay, let's try the next one. All we're doing is examples today. No new ideas, just applying them to new situations. So we got ourselves a 36 centimeter by 36 centimeter square piece of tin. So 36 by 36. Okay. And we want to fold this into an open-topped box. In order to do that, we actually have to cut out the corners. So we're going to end up with this box. Okay, it's going to kind of look like, oops, missed there. Kind of look like that, which has no top on it. Okay, each of the sides used to be over here, right? They were folded up. And a side over here was folded up. Same thing with the front and the back. But to do that, we actually have to cut out each corner. What size square should be cut to maximize the volume? So we're going to cut out a piece that's got to be x by x. We don't know how big, but we know they're squares. Well, if I cut that off each corner, I start off with 36 from here to here. And if I cut off x amount from each side, I end up with 36 minus 2x in the middle. And because we're doing it from all the sides, this piece will be 36 minus 2x also. And so will this one, and so will this one. Because you're cutting off an x from each of the side pieces. And because there's one on each side, you're cutting off two x's. We want to maximize our volume. What do we know about volumes? We know our volume equals length times width times height. How long is this box? Well, it's 36 minus 2x. How wide is the box? Well, it's a square, so it's the same. The only trick is, how tall is the box? So when I fold up that edge and make that box that goes this way, well, the piece that got folded up used to be down here, right? And how much did we cut off? We cut off an x. So when I fold it up, the height of that is also x. Yeah, that's kind of your tricky thought for today. Okay, now I want to maximize my volume. Good news this time, I've only got one variable, but it's a pretty messy equation. So let's simplify this before we try to optimize it. Let's expand our brackets. Let's do some FOIL. 36 times 36, 1296. 36 times 2, 36 times 2, 2x times 2x. And don't forget, all of this needs to multiply with x afterwards. Okay, so I'm going to do both at the same time. I'm going to collect it, multiply it, and actually put it in the right order. So I'm going to do this first. So it'll give me 4x cubed. Together it makes 144x. Times it by the other x, I'll get 100, oops, sorry, it's a minus sign, minus 144x squared. And I can do this one too, and I get 1296x. There is an expression for volume in terms of x. I want to maximize this, which means I want to optimize this. So in other words, I want to take my derivative and set it equal to 0. So 0 equals. So our power law, we've got 12x squared minus 288x plus 1296. I need to solve this. Now you can solve it using your Poisson function, your graphing calculator, or you can factor it, or you can use the quadratic formula. Your choice, I'm not really picky. I just need to show the factoring way. So we divide everything by 12, and we'll get 108, I think, for the last one. Okay, it's a trinomial, so what adds to 24 and multiplies to 108? And we end up with, what do we got there? 6, and 18 will work. So our zeros, our solutions, are either x must be 16 and x must be 18. Well, how can we get two solutions? That doesn't make sense. One of these must not work. So if you go back to the beginning, what were we talking about? We were talking about cutting a piece off of a 36 centimeter wide piece of tin. And we're cutting a piece off each side, right? The size of x. Well, if I start with 36 centimeters and I try and cut off two pieces that are each 18, 36 minus two pieces, each 18, I end up with no 10. Kind of a problem, wouldn't you think? So this answer is inadmissible. There's nothing left over if I try that. It's not a practical answer. So each corner piece is 6 centimeters by 6 centimeters. Okay, that's again a idea of how we can use calculus to optimize a situation involving a three-dimensional shape. We're only going to deal with rectangular prisms and cylinders. Only two shapes you guys have to worry about. Okay, so we did two rectangular prisms. Let's try ourselves a cylinder. So we got a closed cylindrical can of height h, radius x, contains 350 millimeters of pop. Now in most cans you actually do 355, but to make it a little bit easier to work with, let's just go with 350 this time. So I'll write down an equation involving x, h, and 350. So what do I know about 350? It's my volume. Well, the volume of a cylinder, that's in our equations in our formula book, is pi r squared h. And you guys don't have to memorize them, but you have to know what they are. We were told the radius was x, so in this case it's x squared, and the height was h. So part A says write down an equation, and there one is. Here's an equation involving x, h, and 350. Part B, surface area in terms of x and h. Again, in our formula books, we get 2 pi r squared, that's your top and your bottom of the can, two circles, plus 2 pi r h. There's your cylindrical lateral surface, the part that wraps around. Now, in our case, our radius was x, so we've got to replace the r's with x's. We don't know the surface area, so we leave it alone. In part C, show the surface area equals this mess. Now, notice that one letter is gone that we used to have, the letter H. What do they do? Well, like the first question we talked about today, they took the first equation and they divided out the pi, the x squared, the pi, the x squared, to give themselves an expression for H. We kind of always want to do that when we have two equations, so we can take one equation and substitute it into the other. So we're going to get surface area equals 2 pi x squared plus 2 pi times x times h. But h is 350 over pi x squared. Now they said make sure it looks like this. So what have they done? They've simplified. So let's do some simplifying. We always want to simplify anyways because it makes our life easier. On top we'll get 700 pi x over pi x squared. Well, we know one of our rules is when you have fractions, anything that shows up on the top and the bottom that's the same can be cancelled out. So we can cancel pi with a pi, one of the x's with one of the x's. And I'll end up with 700 over x. There's an expression for surface area, just the way they wanted. Part D, find the value of x and the corresponding value of h to make the surface area a minimum. Hey, there's my optimal situation. Let's minimize, which means take our derivative equal to 0. We know before we do that though, we should make our equation easier to work with. Bring that exponent up, and then we can take our derivative and set it equal to 0. At this point, it basically becomes the same question we had before with the rectangular prism, just we got more complicated numbers because we have pi's in there. Okay. 2 times 2 makes 4. Pi is a number, don't forget, so we can just have it as 4 pi x. Okay. It is, yeah, 3.1415, but instead of writing the whole big long decimal, let's just use the pi symbol in there. Okay, minus 700 x to the negative 2. Okay. I want to solve this, so I'm going to fix my exponent all over again. So put it down the bottom. I'm going to set it up for cross multiplying because that's what we do when we want to solve these things. I'm going to cross multiply. So this way, give me 4 pi x cubed. Now I've got to solve this. To solve it, I got to get rid of this number part. So I'm going to keep it exact for now. So I'm going to divide both sides by 4 pi's. So on the right, we'll get x cubed. On the left, we'll have 700 over 4 pi, whatever that comes out to. I'm not really worried about the number yet, because I'm going to have to take a cube root of whatever 700 over 4 pi is. And if you want to put that on your calculator one time, you can. Just put brackets around it all. So we're going to get an x value. We put it all in our calculator properly, hopefully of 3.82. Okay, give it a try. In part D, they also asked us for the height. The h value makes this true. So let's use our equation here. H is 350 over pi x squared. I'm going to move down further. H equals 350 over pi x squared. But we just figured out the optimal value for x. So pi times 3.82 squared. Put that part into our calculator, we end up with 7.63. There's our optimal h and our optimal x, which is what part D was asking us for. Part E, find the minimum surface area. So you've got all these equations for surface area you can use. Again, the one we started with, we simplify that to this form. Okay, we simplify that to this form. We have all these forms you can pick from, right? I'm going to use this one. Okay, so my surface area, this is part E now. My surface area was, sorry, I have to go back up for 1 second here, 2 pi x squared. I'm just going to write it down. 2 pi x squared plus 700 over x. Just check that. Yes. And what do I know? I know x. It's 3.82 squared. So I'm going to replace both x's with 3.82s and plug it all in my calculator, and hopefully you guys got 274.93, or if you go 3 sig figs, 275 centimeters squared. Okay, and that's our last optimization question. It's a cylinder. As I said, you guys are responsible for rectangular prisms and cylinders, and you got to be pretty comfortable. Pretty much a guarantee you're going to see one of these down the road more than once, and have to be able to do with those parts. So if you're stuck with something, come see me. Try the couple homework questions. Don't worry about making sketches. It asks you to sketch them. I'm just worried if you can solve them or not, find the optimal values. They do follow some of the same procedures all the way down in terms of once you take a derivative, you always set equal to 0. You set up for cross multiplying, all those basic things. But if you're stuck, come see me, please.